when you have that, okay, when you have that unhybrid p orbital, after the sigma bond forms, the two p orbital, one from each carbon, they get closer to one another in parallel position, and the parallel overlap of two p orbital, it gives a pi bond. A pi bond by itself is weaker bond compared to sigma bond. So we have sigma here, and this is like a pi bond. Pi bond, it's like a overlap on the top and then overlap bottom. So basically a half pi up, half a pi down, but together is like one pi bond that is forming. It is weaker overlap or weaker bond that is forming because you see there's a space in between the two p orbitals. Basically, when there is a space, that means there's restriction. More restriction, electron doesn't spend more time in that area. Electron can only spend time or be in the other area of the PP side-by-side overlap. And because it's restricted, it's going to put more pressure on the electron. It's going to make it more energetic or less stable. Because it's less stable or weaker bond, if you break it, it's going to take less energy to break it. And that's how you can actually break the pi bond in hydrogenation. Let's say you add H2, you break the pi bond, and you change that to two new sigma bond. We talked about the geometry is 120 because it's sp2, so 120, all these are 120 around carbon that has double bond. Hybridization is hybridization is sp2, and the bond angle is 120. When it comes to strength of the single bond versus double bond, single bond is longer, but CC double bond is stronger. So the greater the bond order, stronger the bond is going to be. So this, we're talking about the double bond. We are not comparing sigma to pi bond. If his single bond is just one sigma, if his double bond is one sigma and one pi bond, and this combination is a stronger bond compared to CC single bond. CC single bond, however, is a longer, has a longer bond length, but the shorter the bond length, the stronger the bond is going to be. Let me know if you have any questions. You can stop me, you can use the chat option, or you can use the mic to ask any questions that you might have. I don't want to ignore your questions, just want to make sure I answer as I'm covering the slides. So we talked about the general formula for alkene versus alkane. Alkane is saturated and alkene is unsaturated. If the carbon has only one double bond, then is missing two electrons. For every additional double bond or for every additional pi bond, there would be two more hydrogen missing. So let's say if you have a compound that it carries two pi bond, okay? If it carries two pi bond, then for four carbon, the number of hydrogen is going to be, normally it would have been 10. And if you have two double bonds, for less than that is going to be H6. So every pi bond takes care of two hydrogen. That means if you have 4 carbon, that requires 10 hydrogen to be saturated, following this formula, C4H10. If you increase the number of pi bonds or double bonds, for every double bond, you're missing 2 hydrogen. If you have 4 carbon with 1 double bond, the formula is going to be C4H 8. So it's missing one set of hydrogen or 2 hydrogen compared to the C4H10, which is saturated. For 2 pi bonds, it's C4H6. And if you had a 3 pi bond, so basically 1 double bond, let's say 1 triple bond, then it's going to be missing more hydrogen, and that would make it H4. So you have, it depends on the number of pi bonds. Each pi bond, it counts as element for unsaturation. So when we are talking about alkene, alkene is known as unsaturated hydrocarbon, but alkane or acyclic alkane, those are saturated hydrocarbons. So we have saturated versus unsaturated. If you have more than 1 pi bond, it's going to be like, it has a new name, and that is polyunsaturated. If it has only 1 double bond, it's called monounsaturated. So you have polyunsaturated or monounsaturated. These are other terms that it's associated with the family of alkenes. C8H14, is this saturated or unsaturated? C8H14. How do we know this is saturated or is not saturated? The general formula for saturated hydrocarbon is CnH2n plus 2. So if N equals 8, okay, if N equals 8, carbon is 8, hydrogen must be 2 times 8 plus 2, and that is 16 plus 2, 18. So if it was saturated, it needed 18 hydrogen to be saturated. So needs 18H to be saturated. But now, how many does it have is 14. So 18 minus 14 is like 4 hydrogen. 4H is missing. So how many elements of unsaturation you would have? The 4 hydrogen missing, that counts for like 2 pi bonds. And that could be 2 double bond, because for every double bond, you get 1 pi and 1 sigma. And if you say 4 hydrogen is missing, that is 2 elements of unsaturation. EU equals 2, element of unsaturation equals 2. That could be 2 pi bond or 2 double bond. It could be 1 cyclic system and 1 double bond, or 1 pi and 1 cyclic systems. Because for cyclic systems, if you remember from chapter 3, we also had a CnH2n. This is for cyclic alkane. Basically is missing 2 hydrogen. So you could have a bicyclo system. For every cyclic, 1 element of unsaturation. It counts as 1 element of unsaturation. So if you have a bicyclo system, that means 2 elements of unsaturation. You could have a triple bond, because for a triple bond, a triple bond is made of 1 sigma and 2 pi bonds, and 2 pi bond counts for 2 elements of unsaturation. So structures A, B, C, and D, these are possible structure, one of the possible structures that for C8H14. So if you count the elements of unsaturation to be 2 elements of unsaturation, then you can predict that it could be 2 pi bond, 2 double bond, it could be 1 triple bond, which is 2 elements of unsaturation. It could be 2 cyclic system, and it could be like 1 cyclic system and 1 pi bond. So unsaturated hydrocarbon versus saturated. Unsaturated, it means that it's missing some hydrogen. It contains fewer than the maximum number of the hydrogen for alkane. Saturated hydrocarbon contains the maximum number of CH bonds. That's example of it is alkane. When you say unsaturated, anything that has a pi bond doesn't have maximum number of CH bonds. So you have a carbon-carbon bond, and it's a pi bond, is going to be unsaturated. So simple, but at least, you know, to make sure that everyone follows the definition and the terms that is needed to study chapter 7. Now, we already practiced, believe it or not, that was a practice that we did for, let's say if you have, this is what we had, H14, and we counted 2 elements of unsaturation. Now, what happens if your molecule contains heteroatom? If molecule counts as a heteroatom, like halogens, Cl, that's equivalent to 1H. So 1 Cl is like 1H. So you have to substitute. And for nitrogen, nitrogen counts like half a carbon. So 1N is 0.5 C. Nitrogen counts as oxygen, do not count. Okay. Do not count the oxygen. So for a compound that is C6H7N, how many hydrogen is needed to be saturated? You have 6 carbon. Can you tell me how many hydrogen is needed to be saturated?
Is it 14?
14. Yes. 14 hydrogen is needed to be saturated. And then you have half a, so in this structure, how many carbons do you have?
6.
Is it 6 or 6.5?
6.5.
Thank you. It's 6.5 because if we have nitrogen in the molecule, that counts as it counts as a 0.5 carbon as well. So if you had,
But wait, why is that? Why does it count as 0.5 for carbon?
Is for nitrogen. Nitrogen is not tetravalent. Nitrogen is a trivalent. So nitrogen is satisfied with three bonds. And the number of hydrogen that is needed to saturate nitrogen is like half the carbon. So by convention, like if you have a Cl, let's say if you have a Cl, CH3Cl, that is saturated, right? You have, because Cl counts like 1 hydrogen. Basically, you have 1 carbon and 4 hydrogen because chlorine counts as 1 hydrogen. So it is saturated. Nitrogen counts as half a carbon. It's just by convention, counted as half a carbon. And if you have 6.5 carbon, number of hydrogen then is going to be 6.5 times 2 plus 2 is going to be 15. So we need 15 hydrogen to saturate, to make sure that the molecule is saturated. We don't have 15. How many hydrogens do we have?
7.
You have 7. Perfect. So you have 7 hydrogens. 15 minus 7.
8.
15 minus 7, it gives you 8. 8 divided by 2, it's 4 elements of unsaturation.
Why do we divide by 2?
Okay. They're all good questions because every elements of unsaturation is like a pi bond. Okay. 1 pi bond. 1 pi bond. Okay. 1 element of unsaturation is 1 pi bond, or it could be 1 cyclic system. 1 pi bond or 1 cyclic system It counts as one element of unsaturation. So if you have a carbon-carbon double bond is 1 pi and 1 sigma, if your molecule has only one double bond, then it has one element of unsaturation. Now, is missing 2 hydrogens. So for every 2 hydrogen counts as one element of unsaturation. We had that in the red color in previous slide as well. Let me see if it was talking about the, see right here, for every 2 hydrogen atom missing, there must be either a pi bond or a ring. And every 2 hydrogen basically counts as an element of unsaturation. So if you have the number of hydrogens that are missing, that is the number of hydrogens missing. And now if you want to find how many pi bonds you have, for example, you have to divide 8 by 2. Number of hydrogen, missing hydrogen, divide by 2, that gives elements of unsaturation. And what counts for element of unsaturation would be a pi bond. It would be a cyclic system. And then I just want to repeat this because if you have heteroatom, nitrogen counts as half a carbon, and halogens in general, not just chlorine, halogens counts as hydrogen. So if you have 2 chlorine, it counts as 2 hydrogen, or other numbers is going to be the same. Okay. So we have 4 elements.
Professor, I have a question.
On saturation. Yes.
So how would you know if it's a cyclohexane or if it's a benzene, and when they're writing it down, I will be able to tell on that sense.
Okay, good questions. Remember for the other example that we had 4 elements of unsaturation. I'm sorry, for the other one we had 2 elements of unsaturation, right? For a previous example, we had 2 elements of unsaturation. Let me go to the other previous one. Here we have 2 elements of unsaturation. If we have 2 elements of saturation, compound A, B, C, and D, these are possible compounds. All we can come up with at this point is say, what are possible compounds for it, or what are the possible structure for this molecular formula? We do not have a definite answer yet. If you have 4 elements of saturation, unsaturation, would that be a benzene ring, or would that be like a for a cyclic system with a triple bond and a double bond and all that? So we need additional information. Usually when you have when you have 6 carbon, a good estimate would be, with that many number of elements of unsaturation, it would be benzene ring. So you have 3 pi bonds that takes care of 3 elements of unsaturation, and 1 cyclic system that's like 4 elements of unsaturation. Then you could have like a, NH2 attached to it that takes care of the whole molecule. So we don't know exactly is it benzene ring or not, but that is one of the possibility. For 4 elements of unsaturation, you could have other possibilities. You could have 1, 2, 4, 5, and 6. You could have, that could be the structure instead of this one. You could have NH2 attached to one of these carbons. So that is a possibility as well.
Professor, that benzene ring you drew has 4 or 5 unsaturations?
Okay, what counts as unsaturation? It's a good practice, a good question. Pi bond counts as 1, right?
Yeah, and the
1
ring
pi
bond.
equals 1 element of unsaturation, and ring, okay? Ring, any ring, not just the cyclohexane ring, counts as 1 also, right?
Mm-hmm.
1 element of unsaturation. How many pi bonds do we have?
3.
And how many ring we have?
1 ring.
So it adds up.
So
So
the group coming off the ring doesn't count as an unsaturation?
the ring counts as one element of unsaturation, and then we have 3 pi bonds that adds up to 4 elements of unsaturation.
But the substituent coming off of the ring doesn't count as a saturation or
Uh,
unsaturation?
This one, no. This because nitrogen is a trivalent. If it has 3 bonds, it's satisfied. So nitrogen has two bonds attached to hydrogen and 1 bond attached to the ring. So it's saturated. This side of the molecule is saturated. It's only the benzene ring and the 3 pi bonds.
If there was 1H, it would be though.
1H?
Yeah, if it was 1H, just NH hanging off, it would be
Yes, yes.
unsaturated.
Yes.
I see.
Mhm. Okay. Nomenclature for alkene. Alkene, you have common name, you have systematic name, and then you have IUPAC name. It's good to know the common names, but you are responsible for the IUPAC name. When you are naming a compound that is alkene, you must start numbering from, you are always looking for the longest carbon chain, but now the priority goes to the functional group of carbon-carbon double bond. So even if it gives you fewer carbon in the main carbon chain, it must include the carbon-carbon double bond. So you start from these are the solved problems. We're going to look at this, and then I put other examples. So you start from the side that is closer to the double bond, 1, 2, 3, and 4. And then you have to indicate the location, because butene, the double bond, it could be on carbon 1 or 2. So you have to indicate, is it 1 butene or 2 butene? Like for the next example, carbon 2 carries the double bond. So the name is going to be 2 butene. And you have to number it from the side that is closer to the double bond. You should never, you're not expected to say like a 2, 3, okay? Hexene, if you say 2, 3 hexene, that means you have 2 double bonds. It's understood that it starts with the lower number and it ends with a number, consecutive number. So if you say 1 butene, that means double bond is between carbon 1 and 2. That is understood. So you just say 1 butene, that means between carbon 1 and 2, there is a double bond. When you say 2 butene, that means between carbon 2 and carbon 3, there is a double bond. So you have that part is kind of understood. Now, the fact that, double bond takes priority over longest carbon chain, we have an example here. If you go from this and from left, right to left, 1, 2, 3, and then 4, 5, 6, 7.
You know, they don't check the paperwork down here in Florida because they just want to find out themselves and let someone.
Okay, so if you find that if you go from right to left, you end up with 8 carbon, but if you start from the CH2, you end up only with 6 carbon. What is correct is to make sure that CC double bond is included. So you have to start from the carbon double bond, the CH2. You cannot start from the longest. You cannot care, or you cannot be concerned about the length of the carbon if the cost is to leave the double bond out. So you cannot leave the double bond out. You have to go from the side or include the main carbon chain in a way that carbon-carbon double bond is included. So double bond or the functional group, it takes priority over the long carbon chain. But again, that becomes just a secondary factor, because if you go 1, 2, you have a choice of saying 3, 4, and 5 if you go to the right side. But if you go to the left side, it gives you 6. That's why 6 is preferred over 5, and you don't go to the right. When you go 1, 2, you go to the site that it gives you the longest carbon chain, but you cannot start from this end, which is, then that is not going to include any double bond.
So the double bond takes priority, right? But if it's a triple bond, the double bond still takes priority.
Good question. You are one chapter ahead. So if you have a double bond versus a triple bond, double bond versus a triple bond, double bond takes the priority. That's kind of unusual. Okay, so the correct name is going to be 1, 2, 3, 4, 5, and not 1, 2, 3, 4, 5. This would be incorrect. Double bond takes priority over triple bond as well. This is one of the exceptions. But double bond takes, triple bond takes over priority over single bond or long carbon chain as well. But if you are comparing double bond and triple bond, double bond takes priority over triple bond. If you have two double bonds, then the general name for your molecule is going to be a diene. So diene, meaning that you have two carbon-carbon double bond. When you are numbering, you have to start numbering from the side that it gives you the lowest number set, just like before, you are looking for the lowest number set. So like in this case, if you go from left to right, the first double bond starts with carbon 2, and the second one starts on carbon number 4. But if you had gone from right to left, it would be 1, 2, 3, 4, 5, 6, and 7. And then you had basically 3, 5 diene, and 3, 5 is not correct because you have, if you go from the left to right, you end up with 2, 4. 2 plus 4 is 6, 3 plus 5 is 8. So you have to go with the lowest number set. And another example here, the only difference is that you have the, you combine the number for the location of the enes or dienes, and then you would say pentadiene. Instead of pentene, you would say pentadiene. Okay, bending is allowed. So in this case, you have to go from the side that it gives you the longest carbon chain because it doesn't interfere with the presence or inclusiveness of this carbon-carbon double bond in the 3-methyl-3-heptene. You go from 1, 2, 3, and then 4, 5, 6. You don't want to go from 1 here because if you go from 1, that's the CH3, there would be 2, and you end up with 6 carbon in the longest carbon chain. If whenever possible, you look for the longest carbon chain. Questions?
Professor,
Yes.
I had a question about nomenclature. For the example you have up there, 5 bromo, 4 chloro, 1 heptene. If you had, let's say, 2 bromo groups, that would be dibromo, but would that put chloro in front of it because of the alphabetizing rule?
No, for the alphabet, for the prefixes, for when you are putting the branches in alphabetic order, you do not use prefixes. So if you had, let me do what you want me. I'm going to put the BR, okay, and then BR, and I put here chlorine and a methyl group here. Okay. So what would be the name for this molecule? Which site should I start numbering? Because I have a high priority, a functional group of carbon-carbon double bond, regardless. Like if I go from here, I would get smaller number set most likely because I have chlorine and bromine in this end. So I
Yeah.
have to start closer to the double bonds. I have to start numbering from the left side. So it would be 1, 2, 3, 4, 5, 6, and 7. Now, I have bromo and carbon 5 and carbon 6. So I have 5, 6 dibromo. So I'm going to just list them. No, I'm not putting it together as a name. So I have 5, 6 dibromo. I have 4 chloro. And then I have 2 methyl. Your question is, if I want to give name and there's 7 carbon in, so it's going to be heptene at the end. And then we have the 3 heptene. Your question is, if I'm alphabetizing this, should C comes before D? Okay, are you counting C and D, or you're counting C and B?
Yeah,
I'm saying D does not count.
gotcha.
So prefixes doesn't count. So if you have a prefix of di, tri, tetra, sec, it doesn't count, with exception to iso. If you had an iso, like isopropyl,
Mm-hmm.
then you would count this one I, not the P. This is the only exception. For isopropyl, you count the I for prefix, but for any other prefixes, you count the actual branch, not the prefix.
Gotcha. I just wanted to clarify that. Thank you.
Sure. So the name for this compound that I have in the red color is very similar to this, with slight difference. We have to give the location and the branches, place them in the alphabetic order, because bromo comes before chloro. So it's going to be 5, 6 dash dibromo, 4 chloro, 2 methyl or 3 methyl, 2 methyl, 2 dash methyl. Sorry, it's going to make it confusing. Let's just 2 methyl, and then heptene is on carbon number 3, is going to be 3 heptene. Okay, so that would be the name. Now, more specifically, when we learn about these, we are going to talk about the cis and trans. Is this molecule cis or is it trans? The cis and trans situation is going to come up when we have 2 identical group attached. So you have like a hydrogen, and then you have hydrogen, you have CH3 here. Okay, so in this case, I would say this is cis, because the same groups are on the same side. But if you have alkene, and then you have groups that they are not identical on the two carbon. So you have Cl and H. Well, you have 2 groups, you have the CH3 and the Cl on one side, hydrogen on the other side. Even if you didn't have, even if this was not the hydrogen, if it was a CH3, then what would you name this? Would you name this one cis or trans or neither? Since these groups are not identical, the groups are on the 2 carbons are not identical. Okay, you have this group. These 2 groups are not identical to the other 2 groups. The new term that is used here is this E or Z? E or Z configuration instead of cis and trans configuration. So in order to determine is E or Z configuration, we have to give priority based on the atomic mass, just like chapter 5 that you give priority based on atomic mass. So you give priority, and the higher the atomic mass, the higher the priority. Since you only have 2 groups attached to it, it's going to be only choice for 2 priority, 1 or 2. In the right side, the carbon on the right, you have 2 groups attached. CH3 takes priority 1 and hydrogen takes priority 2. So I have a 1 and 2. On the carbon on the left side, chlorine versus CH3. So the first element attached to chlorine, that's mass of 35, that would be 1, but carbon here is going to be 2. So when you say CH3, actually the carbon is attached to carbon, not the hydrogen. So CH3 is a CC bond. So carbon is lighter than Cl, so Cl takes the priority. Now, if the same priority are on the same side, so we cannot call it same group here because one is Cl, one is CH3. If the same priority are on the same side, is going to be called Z, and Z is coming from a German name, but if you want to make it easier for you to remember, you have to read that like as a same, like a same on the same side. So the priorities are on the same side. So it's going to be Z designator or Z confirmer. So we have the Z designation for this molecule. So now if you want to, since we have like a 3D structure here, if you want to determine the priority for these 2 carbon, we have chlorine, priority 1, and this carbon, because it's carbon, is going to be priority 2. So 1, 2. And then you have hydrogen here and carbon. So hydrogen is going to be 2. This carbon is going to be 1. Now we have same priority, okay? Same priority on the same side, and since there's only 1 double bond, you can just say here Z. Priorities or same priority on the same side, so we designate as Z. Z5, 6. Can you determine for this structure this is the E or Z? No. So it depends on how the structure is given to you. If the 3D structure is given, this designation of a Z or E is expected. But if the condensed structure formula is given to you, you cannot determine if it's Z or E, and you just give plain name to it. If a double bond is in the part of cyclic system, is understood, and this is part of the rule, that carbon-carbon double bond is going to be between carbon 1 and 2. Now, what happens if you say this is carbon 1 and not this one? If you say this is carbon 1, then you must say carbon on the left is 2, and then 3, 4, 5. If you start with this as a carbon 1, then ethyl group is going to be on carbon number 5, which is a high number. That's why you cannot start from this carbon as a carbon 1, and you just say carbon 1 is the one to the left. So you have 1, 2, 3. So that would be 3 ethyl cyclopentane. Do I have to say 1 cyclopentane? No, because it's understood that carbon double bond is between carbon 1 and 2. So we don't have to bring that 1. We only say ethyl group is on location 3 with respect to the carbon-carbon double bond. In this case, you have 1, 2, and if you say cyclohexene is already understood, that is carbon double bond is between carbon 1 and 2, and 2 methyl group. Now, would it make a difference if you go from 1, 2 or not? If it doesn't make a difference, then it's going to be the same. But if it makes a difference, you have to start from the side that is going to make, is going to give you the lowest number set. Okay, for this one, if you start with this carbon 1 here, it would be too high of a number, so you have to start from this carbon. 1, 2, 3, 4, 5, and 6. So you have methyl group on carbon 2, ethyl group on carbon 4. Because of the alphabetic order, ethyl comes before 3, and you give that. Okay. The term of cis and trans, when does it exist, when it doesn't exist? That's important for you to know. If you have a group that is like CH3, H, and then on this side you have CH3 and CH3. Is this cis or trans, or neither?
Neither.
Neither, because it's not, we don't have one of the conditions. There are two conditions for cis trans. Condition 1, you must have CC double bond, okay? You must, the molecule must include or contain a CC double bond. Second condition, the groups attached to each carbon must be different. In this case, the CH3 and the other CH3 are equal. Since they are the same, so it's going to be neither. So not cis or trans. Cis trans does not apply to this molecule. You just say it as like a 2-methyl-2-butene. So 2-methyl-2-butene, because that's the name. You cannot say cis or trans. Question.
Yes, what if it was CH3 for all of it? What would it be called in that situation?
Then you would say 2,3-dimethyl-2-butene.
So it wouldn't
So you have
be,
to go 1, 2, 3, 4.
but it wouldn't be E or Z?
E or Z, no, because they are the same again. That you don't have high priority, low priority.
Oh, so in that case, it was just, you wouldn't put anything.
Nothing, no, you don't have to. It
Okay.
does apply, yes. And you might get a question like, which of these molecules cannot have E or Z or cis and trans? Like if you see two groups are identical, it's not going to form, is not going to have E or Z or cis and trans, because if you flip this, the name doesn't change, it's the same, structure doesn't change. So here are other examples of the molecules that they cannot have cis-trans isomers. There is not cis-trans isomer is not possible. But if you look at the ones with the chlorine, then you do have cis-trans possible, because the two groups here are not identical. We are not talking about these two groups because they are on two different carbon. We are looking at the groups are on the same carbon, they are not the same. So it's going to be possible to have cis or trans. The trans is more stable, okay? Trans is more stable. Cis, in case if it's polar, in case if it does have a polar bond, is going to also be more polar and is less stable. So trans is non-polar because the charge distribution of the electron is going to be more symmetrical. It's pulling to opposite direction. But the cis, both chlorines are pulling electron to the same side of the molecule, is going to make it more polar. If you have polar versus non-polar, okay, polar versus non-polar, how would you see in physical property? What's going to happen to its physical property? Example like boiling point. Boiling point is shown there. So boiling point, it depends on the intermolecular forces for the compound. Intermolecular forces, you could have van der Waals forces for all molecules, and for next one in the line is a dipole-dipole. Dipole-dipole exists among only polar molecules. So the cis is going to have dipole-dipole interaction, but trans, because the polarity is 0, the molecule is non-polar, doesn't have dipole-dipole interaction. So cis is going to have stronger intermolecular forces. As a result, boiling point is higher. Dipole moment is 0 for trans. Dipole moment is non-zero for cis. Boiling point for cis is higher because of the dipole moment.
So our cis are gonna be less stable than the
Yes.
trans one?
Trans is more stable. Trans is
Okay.
always more stable than cis, yes. Okay, cis and trans, in this case, it doesn't apply again. We don't use cis and trans because the groups attached to the same carbon are not exactly the same. Instead, E and Z is used. So which one is E? Which one is Z for the molecule on the right side? For this one, is it E or Z?
That one is E.
Okay, let's see. So you determine the priority. The priority for chlorine is 1, for methyl is 2, priority for bromine is 1, and for hydrogen is going to be 2. Same priority are not on the same side, so it's not same. And if it's not same, is not Z, is not equal, so it's going to be E for this one. And the other one most likely is going to be Z, but we are going to try it, is 1, priority 2, priority 1, priority 2. Same priority are on the same side, so it's going to be Z for this stretch. So you have to, if the groups attached to the carbon-carbon double bond, to each of the carbon, if the two groups are not identical or they are not the same, then you cannot use cis and trans. You have to use E and Z designation for it. Any questions about E or Z designation? Okay. So other examples or more examples for the E or Z. Which one takes the priority? What's priority for propyl group here? This priority, is it 1 or 2? How would you determine it? We go from the first atom connected to the carbon first, because it's carbon and carbon, we cannot decide. So you move one bond away, the next one you have carbon, and here you have oxygen. Oxygen takes priority over the second carbon because we could not determine from the first carbon. You have to move away until you find the point of difference. So you're going to have 1, 2, and this one is very obvious. It's 2, and this is 1. Why is very obvious? Because you cannot decide based on the first carbon, but the first carbon is attached to chlorine. This first carbon is attached to another carbon, and that carbon is attached to chlorine. So we are not going to look at this to be like very bulky. We are looking at the one step at the time. The carbon is attached to the chlorine. This carbon is attached to another carbon. So you just move one step at a time. You don't have to move to the third step, because on the second step is already determined that the top one takes priority. And since the high priority groups are on opposite side, it's going to be E isomer. Now, how do we determine? These are the same group, so determining priority is basically the same. When it comes to these two, the first carbon is not the point of difference, right? The second one, so we cannot decide based on the CH and the CH2, then we have to go further down. When we go further down, we have a CC single bond. Here we have CC double bond. Double bond takes priority over single bond because it's attached to two other carbon.
That's a bit confusing. Does that one have a higher atomic mass, or that one has a less atomic mass, right? It just has a double bond giving it priority?
Okay, when it says, if you read this part here, if you have double bond or triple bond, treat it as if it was singly, okay? If it was singly bonded to two of these atoms.
Okay, so you treat it like it's bonded to two CH2s.
Yes,
Okay.
it's bonded to two CH2s. But is it, if it's bonded to another carbon is priority, or if it's bonded to another oxygen?
I would say oxygen.
Oxygen. That's why between these two, okay, between these two, this would be one and that would be two, because first one you cannot decide. Based on the first CH2, you cannot decide. Based on the second one, the second carbon is attached to other carbons. The second carbon here is attached to oxygen, and that's what makes it high priority. So we have 1, 2, 1, 2, same site.
So basically, you want to keep moving over until you find a priority.
Exactly. You find a point of difference. And what is the point of difference? Like if you have one carbon that is attached to two hydrogen, the other carbon is attached to two carbon. You have one carbon that is attached to one carbon, the other one attached to two carbon. But if you have one that is attached to four other carbons, but one is attached to chlorine, the one attached to chlorine would take the priority.
That's
So-
because it weighs more, right?
Atomic mass, yes.
Okay.
Atomic mass of the immediate or the next immediate bond, yes. Between hydrogen and deuterium, which one takes the priority? Hydrogen is atomic mass 1, deuterium is atomic mass 2. That's why D takes the priority. Between the C attached to CH here, this carbon attached double bond versus single bond, double bond takes the priority. So it makes it molecule as a E molecule.
And can you go back real quick? I just had a quick question.
Sure.
For the E isomer, you're not counting the methyl group attached immediately to the CH in the bottom right, are you? You're just counting the last methyl group or comparing?
Okay. We are, in this case, you can say that you have a CH double bond, you have the CH single bond. You have to move one bond at the time. This is like one bond. So you are going one further away.
Yeah.
And one
Okay.
further away. Because if you go that is a different direction.
Yeah, yeah. All right, I see. Thank you.
You're welcome. Okay, so this is all nomenclature. Nomenclature, if you learn from chapter 3, we are looking for the highest number of branches. We are looking for lowest number assigned to branches. We are looking for the longest possible carbon chain, making sure that functional group of double bond is included in there. There is a cis-trans term that applies if the two groups attached to the carbon-carbon double bond are similar, is going to be a cis or trans designation. But if the groups are different, they are different nature, is going to be E or Z designation. In order to determine if it's E or Z or cis or trans, the structure formula must be given. A condensed structure formula, it doesn't provide enough information for you to say if it's cis or trans or E or Z. E or Z is based on the priority. And for the priority group, you look for the element directly attached to the carbon double bond, carbon with the double bond, and you move one bond away from until you find the point of difference. If you have a double bond versus like single bond, double bond takes the priority. But if you have a carbon double bond, but on the other side you have carbon oxygen bond, oxygen takes the priority because one is counted again to carbon, the other one is attached to oxygen or chlorine or bromine. Any questions? Some of the uses of the alkene is you can oxidize it, you can reduce it, you can, because you have a carbon-carbon double bond here, and double bond is made of one pi bond, one sigma bond. It's very easy to break that pi bond. And if you break a pi bond, hemolytically is going to give like two free radical. If you break it heterolytically, it's going to give like a plus and minus charge. Okay, let's say you bring a, if you break this to one side, it's going to be negative and positive. If you break it hemolytically, okay, if you break hemolytically, it's going to give you two free radicals. So either case, you end up with more reactive intermediate. So when you have carbon-carbon double bond, there are a lot of possibility to have addition reaction, to break the pi bond, and you can add multiple different functional group. You can always saturate it by adding hydrogen to go back to alkane. So it depends on what you want to make. So the other application for it is polymerization. You can polymerize alkene to get like polypropylene. That's a polymer, a simple polymer. If you have vinyl chloride, you would get polyvinyl chloride. So it's the polymerization of this alkene, and you get PVC, polyvinyl chloride. That's like has, you know, is a very versatile product that is used in plumbing as pipes and a lot of uses. Then you can use polymerize, you get Teflon. So it depends on the product that you want, but it all goes back to presence of weak bond is called the pi bond here. You can break it and you can add new bonds. So you can add inorganic molecules to it. You could add water, you could add alcohol, you could add halogens, you could add like HCl. If you add HCl, you add H to one and you add Cl to the other one, you end up from alkene, you go to alkyl halide. So a lot of different possible reactions. So there are a lot of uses. You learn about these reactions, the actual reaction in next chapter, chapter 8. But in this chapter, is just have an idea what you can do with this. And with this crowded slide, you get an idea that, yes, there is a difference between alkene and alkane. Alkene, they are more reactive than alkane because alkene has a pi bond and pi bond is weak. It's very easy to break the pi bond and add something to it, just like doing polymerization. When you make a polymer, you basically repeat the same molecule over and over because it's going to attack to the same, and then it would continue as a chain. You see, you have your carbons in the PVC. You have every other carbon has a chlorine. Basically, it's repeating of this monomer. So you have your monomer is linking together to make that polymer. And it's a big deal, making of a polymer, it is a big deal. So there are a lot of commercial uses for these reactions. Which alkene is more stable? A or B? Which one is more stable?
I would say B.
B. And how did you say B is more stable?
From the energy to the side.
The amount of energy that was released is
Yeah.
less. That means, thank you, that since the amount of energy released is less, that means it's more stable. And you don't have to, from now on, for alkene at least, you don't have to know the value for delta H. Instead, you can just know the pattern. Like if you have a carbon-carbon double bond with 4 hydrogens attached to it, this is known as a 0R group alkene. So it's a 0R. And then if you have a CC double bond with 1 alkyl group attached to it and 3 hydrogen, this is known as a 1R. If you have CC double bond with 2 alkyl group, well, it depends on the 2 alkyl group. They are going to be on the same carbon, and then you have 2 hydrogens. And you could have 2 alkyl group, one is in the cis position, the other one in the trans position. So you have 3 different conditions or options when you have 2R. So this is a 2R, this is a 2R trans, and then you also have a 2R cis. So CH3, hydrogen, this is a 2R cis. Okay. Now, what would be 3R? 3R would be like, this is a 3R. Okay, we have R group attached, 2 R groups on the other side attached. So this is like example for 3R. And then what would be a 4R is like you have 4 groups attached to the no hydrogen, basically. Based on this heat of hydrogenation, they have found that if you have a 4R is more stable than the 3R, more stable than the 2R. So 2R trans should come first, right? 2R trans is more stable than the 2R cis. And that is more stable than the other 2R. I don't know what to call 2R gem, okay? 2R gem. Gem meaning that the R groups are attached to the same molecules like a geminal R. And then more stable than 1R.
So basically, the less hydrogens are involved, the more stable it becomes.
Yes, the more substituted, the more stable. So this is called highly substituted. This is called least substituted. Okay, highly substituted. The more substitutions around, the better or the more stable. This is known also as the, let me see if the spelling is in the other. So by comparing the energy for all of them, a double bond has been saturated to change to alkane, and the amount of energy released for 4R is less than the 3R and then the others. So we learned about these in next chapter when we do chemical reactions. When there is a choice of formation of 3R versus 2R, a 3R would be a major product and 2R would be minor product. Because for the 3R, and we had that actually in chapter 6, we talked about Saysef product, and then we talked about the Hoffman product. So Saysef meaning that Saysef product, it means higher substitutions on the alkene. So it's more stable. Okay, for the alkene, if you have if you do have a bicyclo system, double bond cannot be on the bridge unless one of them has like 8 carbon. So that's very minor point. Polarity, we talked about the pi bond. Polarity of cis is more polar than the trans. And to prepare alkene, E2 mechanisms, E1 mechanism, they both give alkene as a product. Dehalogenation or dehydration of alcohol. Those are the methods that it can be used for preparation of alkene. And for elimination, leaving group from alkyl halide, leaving group would leave, and you bring a base to remove hydrogen from beta carbon. Now, if the base that you are bringing is a bulky base, it would go for the least substituted hydrogen. But if it's not a bulky base, if it's not known as a bulky base, then it would go for the more substituted carbon to remove the hydrogen from, because wants to make sure that the alkene that is produced is going to be more stable alkene. Removing of the base and leaving of the leaving group, often it happens from the opposite end, so from two opposite direction. These are other examples of the bulky base. So you saw the T-butoxide, diisopropylamine. This is example of is used in organic too. So you know where it's coming from. Is a diisopropylamine is a strong but very bulky base, and triethylamine. So these are all the amines are basic, and these are the bulky bases. If you have one of these, it would reach for the least substituted beta carbon. So we have Hoffman product, least hindered. Okay, hydrogen is going to be abstracted by a bulky base, and it would give you Hoffman product as the major product. But for a not so bulky base, the hydrogen from more substituted carbon is going to be removed, and the major product is going to be Zaitsev product or Zaitsev product. Questions? So it's just emphasizing again that the removing of the base with the leaving group is going to be anti-coplanar, is going to leave from the opposite side. Okay, rearrangement of carbocation. We talked about the rearrangement of carbocation before for E1 mechanism that was covered in chapter 6 as well. When leaving group leaves and there is a chance for rearrangement, rearrangement that is going to give a more stable carbocation, rearrangement can happen by hydride shift, or it can happen with the methyl shift. In this case, there is no chance for rearrangement because the carbocation that is forming here is a tertiary carbocation. So if there is a hydride shift, it's going to change to primary carbocation, and it doesn't make sense. So hydrogen is removed, and the electrons are dropped in for the formation of a carbon-carbon double bond. So there is no chance for rearrangement. For tertiary, alkyl halide would go faster than secondary. Primary and methyl, it's not going to go through E1 mechanism because carbocation, formation of methyl carbocation and primary carbocation is very low. Possibility of formation of it is very low. If it's an E1, you don't have to have a strong nucleophile or a strong, you don't have to have a strong, yes, you need a weak nucleophile for E1 mechanism. When there is a carbocation, sometimes you get the formation of the substitution reaction also. So E1 with SN1, you could get like impurities or byproduct of the E1 SN1. The product that is forming is a Sasov product. So the other method for preparation of the alkene is cracking. It's called cracking of alkane. So if you crack alkane, if you write a molecular formula, it's probably makes more sense. Let's say you have C18 and H what? 36 is going to be 38, right? Let's say you apply heat and catalyst, and you want to break this like evenly to 19. It could be, it doesn't have to be 19, it could be like 20 and 18 or 90 to 19. So if it's C19, how many hydrogens is needed to satisfy this? I'm sorry, C9. How many hydrogens do you need?
20.
20. Plus the other 9 carbon. How many hydrogen is left for the other one? Is not how many we need. How many is left?
18.
18.
18 is left. So this is a CnH2n, and that is alkene. So if you do cracking, you get one of the product as alkene, one alkane. Now, what happens if you have this C18 with 38? You apply heat, you also do H2 and add heat and add catalyst, because you have to use catalyst for this, definitely. If you get C9H20 plus C9H, do we have to stay with 18? We do have hydrogen coming in also, so we don't have to, because if the alkene forms and there is a hydrogen present with the catalyst, it will go to 20. This is called hydrocracking. So with cracking, you would get alkene, but if it's hydrocracking, you would get 2 alkane with shorter carbon chain. And it doesn't have to be C9. I really don't know. A chemical engineer would decide what pressure, what temperature they should apply to get the cracking at like a C4 and C14 versus C9 and C9. But in general, it doesn't matter if it's a C4 and C14. If you don't provide hydrogen, you will get 1 alkene and 1 alkane. Or often you get mixture of product, but for industry, they can separate those. It's worth it because it's in high scale. It's if the product is produced in large scale, then it's worth it to purify it. But if it's not large scale for lab scale, synthesis in lab scale, cracking, hydrocracking is not a preferred and is not a good technique at all to be used. So cracking, that's another method for preparation of alkene. Okay, your questions. I'm going to stop the recording. I just want to make sure that I have more